This is the last section in chapter 3 we'll look at. 3.10 is linear approximations and differentials. So again, we have a different application of derivatives, linear approximations and differentials. So these two things are related. We're going to tackle them separately. It turns out really this chapter, it's about linear approximations. But we talk about we talk about differentials as well, because this is a great time to finally bring up this topic. So differentials, that's where we get the word differentiate, right? So differentiable. The differential is a much bigger topic than just linear approximations. Although it's kind of a different way to look at linear approximations, it's a great place to introduce differentials, but we're definitely going to see that in the future when we finally get to integration, we will work with differentials again. So we're going to get a flavor of differentials here, but really this section is about linear approximations. Okay, so what is going on here? So we're going to, again, kind of start with linear approximations, just talk about that for a little bit. This is a great time to just kind of introduce this idea with like an example, like a discovery kind of example. Then after we do this example, we're going to look back on it, make sense of it, and we're going to piece together a very efficient, quick like formula that we can get to that answer, or an answer to a similar problem much faster than the way we kind of discover the process. Okay, so the first introduction here in this first example, we're like discovering that this is even possible. Then we'll go back, put a formula to it. Okay, so by hand, approximate the square root of 4.37. Why would we want to do this? So we're going to use calculus to do this, of course. Not a small part of calculus and learning calculus, you're kind of retracing history. So you're going back to when it was first discovered, obviously long before calculators or computers. And we're just kind of, kind of going down the same path. And that gives us, obviously more applications of calculus, but, we're never going to, a bigger reason why we do that, we're never going to be able to progress technology if we don't go back and retrace those same steps of the first couple of 100 years. And something like this would have come very early on after calculus was developed. So they would have had the need to, get really good approximations for square roots of things like this. They didn't have calculators. Actually, what we're going to discover is even, how calculators, what's actually happening inside of the calculator, right? So we're going to get some insight there. Okay, so by hand, let's approximate square root 4.37. Here's what we're going to do. I've got the graph here. I'm graphing the square root of x. So it kind of comes up in curves, in such a way. And notice I've identified the point at 4, 2. That point there at 4, 2, well, 4 is pretty close to 4.37. Actually, let me further my drawing here. So I know when x is 4, square root is 2, but we don't want, 2. We want square root 4.37. So I'm going to put, this is exaggerated just so we can get a visual. Let's put 4.37 out here. So the actual y value we are interested in is right up there, wherever this occurs. Okay. And there's this nearby point. Actually, 4.37 would be very close to 4, right? How are we going to be able to approximate this y value on the square root graph? Okay, here's what we're going to do. Well, use calculus, right? Use derivatives. We're going to use the tangent line. So imagine the tangent line here. And I'm going to try to draw this, and it just barely passes by, and it it barely misses this point, right? I think I'm instinctively like bending this line upwards to get a little bit more space there. But there's the tangent line, right? So it passes through here at the point 4.2. Over this way, we can see, okay, 4.37 is there. And that's where I've put my question mark. How are we going to get this approximation? Check this out. What if we found that y value on the tangent line hey, I can find the equation of the tangent line, right? Like, we can get the equation for that passing through the point 4.2. Well, once I know the equation of that line, it will be very easy for me to get the y value on the tangent line. I just have to plug in that x coordinate into the equation of my tangent line. And that's going to be very, very close to the square root of 4.32, just a little bit above it. I mean, and this is pretty exaggerated, and it's still just a small gap. Let me zoom in. So, you know, we've got kind of this portion that we're trying to look closely at. I've drawn it a second time, if that is helpful for some, down here. And so picture this. So here's the square root of x, and I've really exaggerated the curve so we can get some good separation. So there's square root x, right? There's 4.2. There's where the tangent line passes through. Okay, so we want to know this y value, right? That's at 4.37, comma, square root 4.37. What is that value right there? Well, we don't know. We can't, that's difficult to get by hand. But if we can get the equation of that tangent line, this also occurs at x equaling 4.37. If we can figure out that y value, that's going to be very close to the y value at this point just beneath it. And it will be plenty well approximated for most practical applications, which is why calculus was developed in the first place. Okay, so hopefully you're with me with the game plan. I'm going to write it out right here. 2 steps to this. We're going to find the equation of the tangent line at the point 4.2. Then all we got to do is plug in 4.37. We'll get the y value right there on the tangent line. That's going to be our approximation. Okay, so let's go for it. Hey, finding equations of tangent lines, no problem. Our function is the square root of x. Let's think of that as x to the 1/2. So we need the derivative of that. Derivative x to the 1/2. 1/2 x to the negative 1/2. Hey, because I'm going to find the equation of the tangent line right there, actually I'm going to write this a little bit differently. It's going to be easier if I think of it as 1/2 square root x, which is, of course, the same thing. Okay, so I have the derivative. Let's leave that right up there. We need to find the derivative value of the x coordinate of our point at 4,2. Okay, so I'm going to plug 4 into the derivative. All right, so that's 1/2 square root 4. Now, this is why I like it in this form here. It's much easier for me to compute this way instead of with the negative exponent. It's my personal opinion. That's going to be 1/2 times 2. The slope of my tangent line is 1/4. And of course, we're going through the point 4.2. So to get the equation of the tangent line, let's use the point slope form. Y minus 2 equals 1/4 times x minus 4. And now here, there's a little bit of a difference between the way we normally do things. Right? Normally, we would put this in y equals mx plus b form. right? We distribute the 1/4 and stuff. I'm not going to do that here. I'm just going to add the 2 over, okay, like that. Y equals 2 plus 1/4 times x minus 4. There's the equation of the tangent line, and I like it in this style. Okay. Now, that was step 1. Step 2, we're going to plug in the x coordinate in question. X equals 4.37, just going to go right in right there. So 2 plus 1/4, 4.37 minus 4. Now at this point, we recognize, hey, we could do this by hand, right? I mean, subtracting, easy. I can multiply 1/4 by 0.37, add 2, like, that's no big deal. We could do this by hand if we had to. And that's really not the point to do this by hand. Just grab a calculator at this point and crunch that out. Even though we said we were doing this all by hand at the beginning, it's totally okay to just grab your calculator here. And hopefully you arrive at this. Y equals 2.0925. And that's our answer. For the square root of 4.37, we know is approximated by approximately equal to 2.0925. Makes sense. It's just a little bit bigger than 2. We did it. Okay. Now, if we were living back in the old days in the 1700s, and we needed to approximate square root 4.37, this would be great. We know we got something that really close to it. It's a little bit bigger than 2, right? But since we live in 2020, and we do have handheld calculators, it'd be kind of fun to compare this number to what our calculator would say, just to see how close we are. All right, so I got my calculator, and just for fun, I'm going to put in square root 4.37 and see what it says. How close is that? Really close. 2.0925, and here I've got 2.090454496, right? It's accurate to the hundredths, and then it's only off by like 2 1,000ths, right? Even the 4/5 is pretty close to the 5 here. So that 2 and that 0 and 2 1,000ths is all we were off by. That is incredible. So I actually wrote that here as well for fun compared to the calculator, and that's obviously what I just showed you guys, like only 2 thousandths away. So if you were, designing some kind of new piece of engineering or trying to build a bridge or coming up with a new tool back in the 16, 17, 1800s, and you needed square root 4.37 for whatever you were doing, man, this number right here is going to be more accurate than probably whatever tool you're using to measure, right? Even if you're measuring in feet or miles. I mean, if you're off by 2 1,000ths of a foot, right? I mean, not a big deal. Okay. Miles, maybe that's another story. A couple thousandths of a miles might be something we can actually see, but if you're measuring in inches or, okay, meters, I mean, it's not a problem. Now, what we want to do is look back on this example and try and get a formula out of this and try and get really make this approach very efficient. All right, so we don't have to go through these steps every time. So if you look back on where this went, so we saw here the equation of the tangent line. That was our first milestone. Then all we had to do was plug in that number. Okay, so here's what we got. Here's our formula. We give it this fancy title called the linearization of f of x at a. So let me show this to you and we'll talk through it. It really just boils down to being the equation of the tangent line at a particular point. I'll explain why we give it this name here in a moment. Okay, so we call it L of x, capital L for linearization. And it's equal to f of a plus f prime of a times x minus a. But all that really is the equation of the tangent line at the point a, f of a. All right. Notice this is in the same form that we left our tangent line in a moment ago. Okay, so we had, no, I'll just write it. We had y equals 2 plus 1/4 x minus 4. And if you think about the different components and how they would match, so x is just x, right? So that stays. But all the other pieces get filled in. So we were thinking of a as being 4. Okay. Which would make f of a, if it's a square root function, the 2. So there's our y value, our x coordinate, our y coordinate of the point 4, 2. And then f prime of a was the slope of the tangent line. All right, that's actually f prime a, the slope at 4. And then all we had to do was plug in 4.37. So 4.3 L of 4.37, we'd plug it in there, we'd compute, we got it. Okay, I'm going to spend a bit more time connecting these in a moment. Let's talk about, the different parts. It can be confusing, like, well, a is an x value, but then we also have x and f of a, and it can be kind of confusing. So is there a way we can, like, describe what a and x are when we look at a problem? So these are not technical definitions. This is just the way I think of it to make sense of it. The x value is what we are trying to approximate. Okay, so for us in that last example, x was 4.37. That's what we're trying to get the square root of. So what's a? A is an easy value to calculate that's near x. So if in our case x was 4.37, an easy, if you will, value near 4.37 is 4, because we're doing a square root. Okay, so we'll see this more. What we're going to do is go through that last example again. Same numbers, same function, but now with our much more efficient approach. So bear with the redundancy. I think it is appropriate with this topic. Okay, so let's say somebody said, okay, let's do this again. Approximate the square root of 4.37. Say, okay, I know I'm going to use my linear approximation formula, my linearization of f of x at a. So I'm just writing the formula down. Right? We say, okay, so what is the function? What's f of x? Well, f of x is square root of x. Okay, makes sense. What is the x value? Well, that's what we're trying to approximate. So x will equal 4.37. All right, what is a good a? And now here there's actually some freedom. Right? Nobody tells you what a is. Well, a, it should be obvious. And questions are going to be written so that it is obvious. But obvious is tricky. What's obvious to one person is maybe not as obvious to somebody else. So I get it. There's some freedom here. But you said, okay, if I'm taking a square root and it's 4.37, the easy value, the closest number to that I can just do in my head is 4. So I'm going to take a to be 4. All right. So, all right. I've identified these. This is where I need to begin. Then I realize, okay, it starts with f of a. So I need to know f of 4. Well, for this function, f of 4 equals 2. So I can put 2 there. Okay, I also need f prime a. Well, that means I need f prime of x. Right? I need my derivative before I can plug in. So I would go through the steps. We already did it. It was 1 over 2 square root x. So I'm not going to repeat that. And then, all right, derivative is great, but what we really want to do is plug that 4 in to get f prime a. And when we plug in the 4, okay, we did this already, 1 over 2 times 2, it's 1/4. And then I can say, perfect, I know how to fill in this, this, and this. So now my linearization formula becomes L of x equals 2 plus 1/4 times x minus 4. So we've got the linearization, which is really just the equation of the tangent line. And then we'll say, all right, to finish the question, I need to plug in my x value right there. So L of 4.37, I plug that in, I grab my calculator, and boom, 2.0925 is my approximation for the square root of 4.37. Okay, we've talked a lot. Last thing I want to just show you guys, why do we give it this name, the linearization? Okay, and it's actually, why don't we just call it the equation of the tangent line? So I'm going to go back to my original drawing. You know, if you look here, we call it the linearization because if we are close to our point, we've linearized the curve. We've taken that curve and we've flattened it out, right? So maybe it's once we get too far away, it's no good anymore. But if we're nearby, you know, maybe there's this kind of window where we've taken that curve and we've just straightened it out, and that allows us to approximate points. So we've linearized square root x. At least it's good for, you know, a little while around our point. So that's where it gets the name. Okay, let's stop this video. More examples in the next one.